Quant explained. Breaking down quant finance concepts. Application of quantum computing in quant finance. Can you give an example of how quantum algorithms might speed up option pricing models?
Currently, we usually use the Monte Carlo method to price the exotic option or option under the non-Black-Scholes Merton dynamic, for example using local volatility as shown on the SABR model. Monte Carlo is an excellent method, especially in the multidimensional case, because complexity does not depend on the number of dimensions, which contracts to the traploid rule for integration. Stanisław Ulam created the method during the Manhattan Project for integral calculation and currently is broadly used in finance. But what is the link between them, Monte Carlo and the quantum computing? Quite simple. We can prove that using the quantum amplitude estimation algorithm, we have a quadratic speedup in the quantum Monte Carlo compared to the classical one. This is crucial, especially for multidimensional case where the complex dynamic to model asset behavior is used. But what does the quantum Monte Carlo look like? First, we should understand the structure of the typical quantum program. We can think of a quantum algorithm as the MapReduce approach from the classical big data. First, we prepare the input data, then we process them in parallel. Finally, we should perform the reduce operator and save the result in a single state or the one with the greater probability. So it seemed natural to try to execute the Monte Carlo algorithm on a quantum computer. The quantum algorithm is similar to the classical one. First, we load the probability distribution of the underlying asset. Next, we calculate the value of the payoff function. It is worth noting that payoff functions are calculated at the same time for all paths. This is an amazing example of quantum parallelism. Then, we have to do an aggregation of the value and calculate the expected value of the option. The last step is to use the quantum amplitude estimation algorithm to extract the option price from quantum computer. As I said, there is a proof that quantum Monte Carlo has a quadratic speedup compared to the classical counterpart. The quadratic speedup sounds less exciting than the exponential one, but the gain is great in the case of multidimensional one. For example, if we need 1 million of the replication in the classical Monte Carlo, we need only 1000 in the quantum algorithm. If a billion in the classical is required, we need only 100,000 in quantum. I think the quantum Monte Carlo algorithm is one of the most important use cases of quantum computing for finance. This is especially interesting for multidimensional model, for example, interest rate modeling or valuation of derivative portfolio when we use Monte Carlo method in single Monte Carlo simulation.
How does quantum machine learning differ from classical machine learning, especially in financial applications?
Quantum machine learning is a promising subfield of the machine learning that combines principles from quantum computing with techniques from classical machine learning. It aims to develop algorithms and models that can be processed and analyze data using quantum computing principles. This approach could offer advantage over the classical machine learning for certain tasks. It is especially promising in the noisy intermediate-scale quantum era, which refers to the current state of development in the quantum computing. In this era, quantum device has a limited number of qubits, are prone to the error, and cannot perform error correction quantum computation at scale. Why is that? For example, the noise in the quantum hardware could work as regularization factor in the quantum machine learning. We can also create a quantum network architecture that use only the qubit connectivity of the current hardware, so that the issue of the current quantum processing doesn't suffer as much. Quantum machine learning is a discipline currently under active development, but some areas are up and coming. First, become randomness play a fundamental role in the quantum measurement according to the principle of the quantum mechanics. When a quantum system is measured, the outcome is inherently probabilistic, even if the inner state of the system is known with certainty. This is especially important for generative model. For example, we can see that handwritten numbers generated by the quantum generative adversarial network are better quality than these of the classical counterparty. The property could be used in the finance to create a new data point on the stock exchange, such as Apple versus Microsoft, which correlation learned on the quantum computer. This could be useful in the risk management and model validation. The other important aspect is energy consumption. Lastly, we have seen a significant increase in energy consumption in a big deep learning models. If this trend continues, the training of AI model will have a significant share in energy consumption. On the other hand, in principle, quantum computers require a little energy through recursive computing. Of course, we need to have a quantum processor at the temperature near 0 Kelvin, and to control operation also require energy, but this is significantly less than the classical computer. So quantum computing promises to reduce the energy consumption of machine learning tasks. Last but not least, and I personally think this is even the most important, is to combine the machine learning with classical computing. We should remember that any quantum programming is differentiable. So if there is any parameter in it, we can always find the derivative of it regarding some loss function. On the other hand, we can write any classical program on the quantum hardware. Normally, we don't do this, because if we can execute something on the classical machine, it's something stupid to execute it on the quantum, but we always can. But if we combine these two properties together, there is a new value, and we can interleave the classical programming with the machine learning, and to do this, the training end to end. And this is something that we cannot do classically, because classical programming is not differentiable. This is a new quality. I use this, for example, in a novel algorithm to price the American option. There, I use a machine learning to model the decision function, which is the heart of the pricing American option problem, and the classical programming describe what we do if the option is executed or not. As a result of these quantum computing properties, we can then find the optimal decision stopping rule by training end-to-end in the method, something similar to the direct classical method, but with better properties. I think that there is a great future for such kind of algorithm.
What challenges do financial institutions face in implementing quantum machine learning for risk? How can they prepare for these advancements?
Financial institutions face several challenges in implementing quantum machine learning for risk management. This challenge can be divided into two areas. This similar to the classical machine learning implementation, and this specific to the quantum computing. Let's start with the second area. First, quantum machine learning is still in its early stage of development, and practical quantum computers capable of running complex quantum algorithms have yet to be widely available. Financial institutions must assess their readiness for the quantum technology, including understanding the potential benefit and limitation of the quantum machine learning for risk management. Because development quantum machine learning algorithms for risk management requires expertise in quantum computing and financial modeling, we must invest in research and development to explore and adapt quantum algorithms. Second, quantum hardware is currently available over the cloud, but the machine is usually in the USA, so we must ensure that their quantum machine learning solution adhere to regulatory requirements. Next, implementing quantum machine learning for risk management requires access to the quantum computing hardware, software tools, and expertise. Financial institutions may need to invest in partnering with skilled professionals with expertise in the quantum algorithm and financial modeling. Both classical and the quantum machine learning require work on the interoperability and explainability. This is crucial in a financial application to understand the factor driving model prediction and to ensure compliance with the regular requirement. Classical and the quantum machine learning model may face challenge in providing interpretable results, especially for complex and nonlinear models.
For more on quant finance, join the CQF Institute now.